Lesson 32, solving linear equations, systems with matrix inverse.
Oh, never mind. I know why.
Okay, if A is any n by n matrix, so it's a square matrix, and I is the n by n, which means it's the same size as A, identity matrix, then A, the matrix A times the identity matrix is going to equal the identity matrix times A, which is going to equal A. Do you guys, have we gone over what the identity matrix is?
No.
Yes, so there's one along the main diagonal. I think that's what it's called, main diagonal. Okay. Okay,
Wait, what about the other numbers?
are all zeros. Yes, so there's ones down the main diagonals, all the other entries are 0. So the multiplicative inverse of a square matrix, in parentheses, right, if it exists, because not all of them exist. Not all square matrices have a multiplicative inverse. So if it exists, is a matrix where the product of how do I write this? Of it and itself. That doesn't make sense. The multiplicative inverse of a square matrix. Oh, so the product of the inverse and the matrix itself. Is the identity matrix. So if I were to take matrix A, square matrix A, and times it by its inverse, and that's how we write inverse, to the -1 power, it will equal the inverse times the matrix, and once you multiply them, you will get the identity matrix. So, in other words, two matrices are inverses if their product equals the identity matrix, the I. So if A times B equals B times A equals, then if A times B equals, wait, what? Oh, and it equals I, then A and B are inverses. Now you can tell if a square matrix has an inverse if the determinant does not equal 0, then it has an inverse. So a matrix has an inverse if and only if, remember the double arrow, the determinant of A does not equal 0. Heidi?
Well, on the equation where it's A times something, is that a D, a -1, or a -2?
Neither.
Well, which is it?
Or none of those.
Well, what is it then?
You mean the matrix A times?
No, above it. That one.
a to the negative 1 power.
Oh, okay, thank you.
She's blind.
If the determinant of a does equal 0, then it is called a singular matrix. Yes, Carter.
Oh yeah. Wait. Okay, call it head first.
Okay, Tan.
So, like, 1111 would be a singular one, and like 6, 8, 3, 4, those would all be singular ones.
Maybe, yeah. I'm not sure. Yeah.
Like, what exactly is the purpose of the determinant? Like, why is it important?
Oh yeah, they would be singular because of determinant 0. It just means that there will not be an inverse. You can't multiply it by anything. Oh, and I'm going to explain why in a second. You'll get it. As soon as I tell you how to find the inverse, you'll understand why you can't have a determinant of 0. Probably guess now. So if A equals a square matrix, A, C, B, D. So going top to bottom. And AD minus CB, that's the determinant, does not equal 0. Then the inverse of A, or A to the negative 1 power, is equal to 1 over the determinant of A times the matrix, where you switch the entries on the main diagonal, so this becomes a D, that becomes an A, and you make the minor diagonal negative. So they stay there, they just go negative, these two switch. So the inverse matrix will be 1 over the determinant of A is AD minus CB. So that makes sense why the determinant cannot be equal to 0.
Yeah.
Because then you'd be dividing by 0, and we can't do that. Times D, negative B, or, yeah, negative CA. And it will be a square matrix. You would just multiply this fraction times each of those numbers. So we can solve systems of equations using this information. So if we have the coefficient matrix, times x. Now x will be the matrix of variables, equals, that's going to be the matrix of the constants. So x is the matrix xyz or xy or however many you have there. So to solve for x, you take the inverse of the coefficient matrix on the left, and times it by the matrix of constants. And that will give you all your variables, so you're able to solve. So I'm going to show you an example. Have you told your mom you can't see?
Yes.
Are you telling me the truth?
Yes.
I'm going to give you an example of a 3 equation, 3 unknown problem. Okay? So I'm turning the page right now. So example, solve this system of equation. Negative x minus 5y minus 2z equals negative 23. 4x plus 9y minus 2z equals 29. And negative x minus 3y plus 3z equals negative 2. So we want to find out what x, y, and z is. We can do a matrix, coefficient matrix. So negative 1, negative 5, negative 2, 4, 9, 2, 1, negative 3, 3. Times it by our variable matrix equals, and then we have our answers, negative 23, 29, negative 2. So in order to find x, y, z, we're going to take the inverse of the coefficient matrix. So we write the matrix and put a little negative 1 there, times the constant matrix. So in order to do the inverse of a 3 by 3, I recommend using a calculator. So we plug in the 3 by 3 into the matrix section and just raise it to the negative 1 power, and then times it by the constant matrix. So let me go in here to matrix. We're going to edit number 1, make it a 3 by 3. Negative 1, negative 5, negative 2, 4, 9, negative 2, negative 1, negative 3, 3. And then I'm going to go to matrix and edit number 2 to be a 3 by 1. And I'm going to put negative 23, 29, and negative 2. Can I show my calculator now? Like, are you guys all copied down? Okay, so what I'm going to do is I'm going to take the inverse of matrix A. So I'm going to go into my matrix. I'm going to name A. To do the inverse, I have to push x to the minus 1. And then I times that by my matrix B, and I get 2, 3, 3. So the x would be 2, the y is 3, and the z is 3. So that equals, you don't.
Wait, so if we don't have, but if at the time we didn't have a calculator.
Come in early in the morning and do that.
Yes, or download the calculator onto your computer.
What if we were in the middle of?
Wait,
We
what?
won't make that till nowhere.
What if you were in space trying to?
Then you need to learn how to use it. Like, you'll need to learn. And there's matrices using the calculator are in labs, usually in your book, so you would follow through an example. Yeah, I would not do this by hand. It would take you forever.
Bajillion years.
Yes, a bajillion years, literally.
What if you had that?
Literally.
Cause you just look.
Oh, wait, I'm ending my lesson.